Well, I've got 10 o'clock, so I think I'm going to go ahead and get started and welcome you all here today. It's been a long time. I'm impressed I actually remembered most of your names as passing back the extra credit quizzes here. So that was good. I hope that you all had a nice Thanksgiving break and got a chance to get some extra sleep maybe and some extra rest. I certainly did not. Quite the opposite. As you know, I was gone actually out of the country. I didn't want to tell you about it though beforehand because I thought, oh, the professor's not going to be there, the students aren't going to come to class. So I had to kind of keep that to myself until um, the basically until the break. But yeah, I managed to surprise even myself a little bit. I was climbing these volcanoes in Ecuador that are more than 20,000 feet high. Is the highest mountain I had ever climbed up until now was Mount Kilimanjaro over in Africa. And Mount Kilimanjaro does not have snow on the top of it. So it's just walking on a trail. This is a little bit different in Ecuador. And so because of this, by the way, this is the city lights of Quito at 3 o'clock in the morning. I took this picture. So because of the snow, they make you go to bed at about 6 p.m. and wake up at midnight to climb these mountains because they want it to be very cold while you're climbing. If it gets too warm, the snow gets soft, right? That creates avalanches. It causes you to sink into the snow, which just takes more effort to walk on it because you're using crampons on the bottom of your feet. So that sort of spikes. It gives you a grip on the snow even when it's firm and hard. So they have you wake up at midnight and start climbing. So this was at about 3 o'clock in the morning. I was taking this nighttime photo of Quito, which is the capital of Ecuador, um, as I was on my way up the first mountain. And then, eventually the sun comes up and you get up to the top at around sunrise. So this picture was taken at about 6 a.m. And this is my group of four of us here making it to that. I was very happy. This is a very difficult thing to do. Cayambe is the third highest mountain in Ecuador. It's almost 19,000 feet high. And in the background, you can see some of these other mountains, which are the ones that we did later. And this was actually just the first one that we did towards the beginning of the trip. You can see we're all on ropes and everything here. That's because if somebody falls into a crevasse, which is if you're walking on a glacier, there can be soft spots underneath you. You don't realize it. You step on it, you break through the snow. You can actually go down a long distance. If there's I've seen these huge cracks in glaciers before that are very deep, and then you can't get out. So you could actually be in really big trouble. So they put you on a rope. You would never go up something like this by yourself. You go onto a rope so that if one person breaks through the snow, then everybody else can kind of help hold them up and then get them out. That's kind of the way this is done. Let's see. That's just my summit photo. I have to always show that one. You can see the spiky things on the bottom of my boots here and my harness and everything else. It was balmy. I'm just wearing a light puffy here at 19,000 feet. I thought it would be freezing, but it was actually really nice and warm as the sun was coming up that morning. So that was pretty nice. And then, oh, that one, oh, that's right. That one I don't think it's going to open for me right now. Let's try this one. This is the second mountain that we did. And this one was a little harder. This is called Cotopaxi. You might have heard of a clothing brand that's called Cotopaxi. It's named after this mountain. It's probably the most famous mountain in Ecuador. It's the second highest mountain. But we were struggling with this one a little bit. And so it was already sunrise and we're not to the top yet. The top is just back here somewhere and we're almost to the top. So I already have my sunscreen on and trying to cover my face as much as, but you really have to worry about getting sunburned on places like this. So because all that white snow just reflects everything up onto you. So anyway, this is the second mountain that we did. By now I was feeling a little better. I was more acclimated to the altitude, which was good. And then there's the summit of it. And Cotopaxi had been closed for a couple of years because it's a volcano. Volcanoes often have, steam coming out of them and the lava flows out. This is actually the crater down here. This is not a cloud. This is the steam coming out of of the creator of Cotopaxi, but luckily it was reopened about a year ago because they found that the mountain was safe enough that it wasn't gonna like explode while people were trying to climb it or anything. So that was good. So that was Cotopaxi. This is the same mountain, but from about halfway up it. So you can see just how intense the sun is, how bright it is. Here's the trail we took over here. And again, you don't want to be on this kind of terrain in the hottest time of the day because the snow could be very unstable as the day goes on. So we climbed this in the morning. This picture was taken on the way down. We were already almost back to the camp at that point. But that's how Cotopaxi looks kind of from the side. And then the hardest one of them all, the third mountain, is Chimborazo. And this one is more than 20,000 feet high. This is the highest mountain I've ever climbed. And this was so difficult. This is actually not the top of the mountain. The top of the mountain's over here. And we got up here. It's the famous false summit. You get up to, you think it was the top, and then you realize, no, there was a higher point that was hiding behind it. And just walking from here over to there just about did me in. Like I was ready to just collapse. It's so hard to walk at 20,000 feet. There's so little air. So I went very slowly behind the other people. I was the oldest person there, by the way. I was trying to keep up with everybody, but no, I did fine. But yeah, that was actually not as easy to see the view because we were literally in the fog up here at the top of this mountain. But anyhow, that is the point that is the farthest from the center of the earth. The earth is not a perfect sphere. The earth is kind of, has a bulge around the equator. It's kind of fat around the side. And so this point is actually farther from the center of the earth than the top of Mount Everest, which even though Mount Everest has a much higher elevation than Chimborazo does. And you can see, I think it's just my camera, but the sun just looks huge. Just like the closest point to the sun on the entire planet is right there. So that is kind of a special thing to see. There's the summit. We could hardly see anything on that one because there is so much fog everywhere, but I still had to sort of show off the top there. And then there's our group. We were cold. This one was very cold. You see that I'm wearing a parka. This is like the heaviest thing you could imagine. It's like insulating and keeps you so warm, and yet it got kind of frosted all over. Everybody's got snow and ice all over them here. So it was kind of interesting to see, but I wasn't that cold except when I stopped. As long as we keep moving, I was fine. And I just took a break on the way to see all this glacier stuff. See these cracks in the ice? That's what can be very dangerous. So they try not to take you, you try not to go in those directions. So I was with a guide, of course. You wouldn't go up this mountain by yourself. You have to know where to go that's safe. And so there's people that have spent their lives climbing these mountains, and they kind of know that that's the place to go. Yeah, let's see what else. That's just a picture of Quito in the daytime from one of our warm-up hikes. This one I actually did by myself. There was no snow here. This is a lower mountain, only 15,000 feet tall, right, instead of 20,000. But this is a 3 million population city. Quito is the largest city in Ecuador. And I just got that nice picture of it. You can see sometimes on the, right there, see where my cursor is? That is, I think that's Cayambe. That's one of the volcanoes that we had climbed as well. So you can, on a clear day, you can see everything. It's just the clouds get in the way sometimes. And it's just one last look at it, kind of what Quito looks like from above. So yeah, so I was there for 2 weeks, you know, and you had to be there that long just to acclimate to the climate, or to the altitude, I should say. I started taking these Diamox pills. This is a medication that helps your body, fools your body into thinking you're acclimating to the high altitude, but then it made me sick. So on about the second day, I was throwing up on the trail, like the second mountain that I did. But because I took that Diamox and kind of got that out of my system, by the time we got to the big volcanoes, I actually felt great. And it was the other people that were throwing up. Somebody was sick on every mountain. I mean, we didn't have all of us feeling good at the same time. It's really that bad. But for me, at least, the worst part of the trip was the beginning because I was trying to force myself to take these pills that are supposed to help with the altitude. But yeah, it was something else, guys. I got to tell you, I had my moments when I'm like, why am I doing this? Because it's hard, pretty hard work, and you get up to the top, and it's exciting, it's thrilling, and the views are great, but it's only temporary. You have to come back down and then go try to climb another mountain. So anyway, we'll see what's next. I don't know. Believe it or not, this is like luxury climbing compared to a lot of big mountains, and that's because there are huts on all three of those mountains that I showed you. There are huts that are situated within striking distance of the top so that you don't have to haul a big backpack in and be in the wilderness for 4 days. No. You can drive in the day before, hike up to the hut, and then just have a 1-day climb. Basically start at midnight, get to the summit around sunrise, and you're back to your base camp again by breakfast, basically. So that's luxury conditions. Like if you wanted to climb Denali, which is the highest mountain in Alaska, and I have not done that, you have to be ready to be camping for 3 weeks, basically, right? And no chance to come back for a shower or to get a nice meal in between or anything like that. You just got to be really, really willing to suffer a lot, and I'm not sure I'm willing to suffer that much. So we'll see if I ever get around to doing that. But anyway, yeah, I decided to give it a go. This was the right time of the year to climb those volcanoes. You generally do them around, it's windier on those mountains in the summertime. So November is a good month, and I thought I've got Thanksgiving week. I'll try to squeeze this in. I do feel bad to have left you guys for that time. I hope that everything went well. I'm sure that Janda, my SI leader, hopefully did a good job keeping you guys busy with some group works and helping you with homework and things like that. But yeah, I'm ready now to spend the next 2 weeks basically full blast, getting ready for the end of the semester here. Yeah, and I've got a lot more pictures. If anybody wants to see any more of them, feel free to stop by my office. I got hundreds of them. I just wanted to show you a couple of highlights there. Okay. Anyhow, yeah, right. Okay, let's change gears a little bit here and think about math, I guess for a little while. Where are we at? I have a few things I want to talk about. If we go to the Canvas page here, I'm going to go into the files section. There is a folder already set up. Maybe some of you have already taken a quick look at this during the break. It's called Midterm 3 Resources. And our third midterm is 1 week from today. And unfortunately, I cannot change that date because we are running out of time quickly. We're just going to have to do it next Tuesday. There's a folder here that has, as always, 2 sample midterms along with the solutions to both of those sample midterms. So I would recommend that everybody here, sometime in your studying, try at least one of them to see where you're at, and maybe it'll trigger some questions or whatever. If you have extra time, you might try both of them. If you feel like that would be helpful. I also put the solutions to the extra credit quiz in here. Okay, so I just graded those quizzes this morning, by the way. Just got back. I can see that there's definitely some issues with it. I'm gonna hopefully have a little time to look at the quiz today. There's a review session video. Let me just click on something here. There's a review session here. Something like 11 problems or so. If you want, you can just read the solutions to it, or you can watch the video. I made a video of this. So if you go to the pages section, there's midterm 3 review session here, the last one. If you just click on that, this one I managed to get it into one file. It's a 3-hour file. Okay, so that's there. However, as I was grading the extra credit quizzes, and I'm actually kind of glad that I gave that extra credit quiz because I could see some issues coming up. I was feeling a little guilty about being gone, and I was grading the extra credit quizzes thinking there's a lot of work that needs to be done here to get ready for this exam. I am actually going to do some in-person review sessions. I did not do this for the first two midterms. I'm going to do some in-person review sessions this coming Sunday and Monday. Now, you don't have to come. If you feel ready and you're on top of things and it wouldn't be of any help to you, or you just want to watch this instead, totally okay with me. It's not a problem. But I have decided that I'd like to try to be a little more helpful with this, since I was gone for a little while. So I'm going to write this down because it's not in the materials. I'm going to do this review session twice because I know that not everybody's always going to be free at the times that I would pick. I'm picking some times here that I think will be good for me and hopefully good for some of you who are interested. So the first one is going to be on Sunday from 4 to 6. These are going to be in this room. So they will be in this room. I'll explain in a second. Yeah, so I'm going to do an optional review sessions. One of them this Sunday at 4 o'clock. And then the second one I'm going to do on Monday from 7 to 9. I normally have office hours Monday evenings, so I'm just going to basically turn it into kind of a little more of a formal review session. Now, here's the thing. I am going to record these as well. So first of all, you already have one here. You can just go off with this. If you're interested in seeing what the review session is about, I will record these review sessions and send you links to them if you can't make these times. Of course, you're welcome to come late, leave early, attend parts of both of them, or attend both of them, whatever you want. I'm going to be kind of duplicating the same stuff, though. Some people will ask me, oh, is it going to be the same review? Probably very similar. You know, I might, if I get to the end of Sunday at 6 o'clock and I'm like, well, there's a few more questions I wanted to go over, I might start with those on Monday. But again, I will send out emails to you guys on Sunday and Monday after these review sessions with videos for them. I'm not trying to make more work for you here, guys. I'm really just trying to be helpful. So if this isn't what you want, you're like, no, I just want to stick with what I've done before with the review packet. That's totally good. Sometimes I think it helps students if there's a live thing going on that they can come and ask questions and kind of be accountable and stay focused. So I'm gonna do that. Okay. So I have the time, and especially since I was gone for a week, a short while ago, I think this would be the kind of the least I could do. All right.
So Thursday, we're still gonna go over new content. It won't.
Yeah, this week we have material to cover. I won't be able to do review lines. That's the problem. Yeah. So, but this will be totally just review. So if you don't come to this review session, you're fine, right? You can still just stick with the stuff that's in the review packet, and I think that should be good.
Do we have the sections what midterm 3 will be on?
Yeah, let me write that down for you. It's in the, well, so the other documents that we have here, final section. Midterm 3 review and the solutions to the review. Let me open up this thing. This is almost in final shape. There's just one little thing missing, which is my extra office hours TBD. I've got to like put those in there. Other than that, you can see the sections that the exam is going to cover. I don't know how easy that is to read. 6.3 and 6.4, right? And then 7.1 through 7.3. And then 8.1 through 8.3, as well as 8.7. And finally, 9.2 through 9.5. So these are the sections that the exam is going to cover. I would give the 6.3, 6.4 stuff, well, let me say 20 to 25% of the midterm would be that. That's the stuff on kernel and range, one-to-one, onto isomorphisms, all that good stuff, right? And then chapter 8 is what we just kind of finished recently. That's probably going to be 25 to 30% of the exam. And then chapters 7 and 9 kind of go together, because after all, chapter 9, what we're learning about right now, we have to find eigenvalues and eigenvectors. I'm going to review this in a moment. We have to find the eigenpairs of a matrix in order to solve these systems of differential equations. So they kind of go together. I would put these two chapters almost together at about 50% of the exam. It's a lot. It's a lot. So the stuff on chapters 7 and 9 will be close to 50%. This is just a rough idea. If you want, you can think of each part as being roughly a quarter of the material there. Yeah.
If we're
Question?
following the book while studying,
Uh-huh.
8.1 through 8.3, we just skip obviously 4, 5, 6.
Right.
Or do they tie into some?
They don't tie in at all. You can just totally skip them. Yeah. Yeah, only these sections here you have to be thinking about. Okay. Yeah, so of course here I've got a review of what all the words are, the important terminology, things to be able to do here at the bottom. This goes on to the next page. It's a big bullet point list. It's a very big list. And then some practice problems here at the end. I wouldn't do these practice problems though, unless you've already done everything else. If you've already done the review session and you've already done the sample exams, then you could maybe look at some of these. These are older questions though, that maybe aren't quite as reflective of what I would be asking you guys about now. But anyway, I've got a few extra problems here. There's like this Romeo and Juliet love story here. I mean, this is really going above and beyond. Like if you really want to model it with a system of differential equations, you can do that. So there's that. Then we've got the ants crawling from this is the Markov process thing with ants crawling from the kitchen to the bedroom. I didn't really give you any homework on that. So again, this would be another example of a problem that you probably don't need to get too stressed out about. So these problems that are in this packet, I would do them only if you've sufficiently looked at everything else and you feel pretty good about everything else. But I put it here just in case you're interested in it. Yeah, so anyway, it's the usual deal, guys. A pretty big full folder of stuff to look at. All of it optional. Do as much or as little of it as you have time. I know you're busy, you've got other classes, you got things going on. I'm not expecting anybody to do all of this. I'm not expecting that everybody's going to just show up in droves to this either. I will record this session though, and I'll be available in person at least for those review sessions as well as my office hours. Okay, so that's kind of the plan. I would like to give you a little encouragement about this, which is that if you work really hard this week to get ready for this exam, right, this third midterm, you are going to have this material so fresh in your mind that the next week that comes along, when we have our final exam, you're not even hardly going to have to study this whole half of the class. It'll just be, oh, I have to go back and review maybe some stuff from chapter 1, or maybe we forgot what inner product spaces are or something like that. But if you work really hard here, right, so much of what's in Math 250B is called upon here in these 4 chapters. So I used to only give 2 midterms in this class, and my students would tell me that, it's just so much material for each exam because there are only 2 of them. So I added this third midterm, and it's kind of at the end, and I know it feels like it's really close to the final, but I actually think that it's worked well to have this at this time because it actually is sort of, you're getting to double dip on it. You're studying not only for this midterm, but it's also going to get you very, very fresh and ready for just 1 week later when we take the final. When we take this exam on Tuesday, I will be grading them like frantically fast and getting them back to you on Thursday. So you'll have all of this stuff to review for the final after that. We only have 2 weeks left. It's really what it comes down to. So are there any other questions here? Yeah, go ahead. Yes, sir. After the midterm on Thursday, we will be partially reviewing for the final. I have one section, which is 9.6, which I need to cover. It only takes about 40 minutes to cover it though. So we'll have at least half of a class to review for the final. Definitely. Other questions, other comments? Okay, so that's kind of where we're at. Now there's also some homework due tonight. I see some problems on the sideboard over here. I'm going to try to save some time to look at those questions as well as maybe go over the extra credit quiz a little bit too. But before I do that, I actually want to cover, we still have not covered 9.4 and 9.5. And I want to cover 9.4 today and 9.5 on Thursday. Okay, so one section each day. that's based on solving linear systems of differential equations. So I've kind of put this up here for us to look at. Let's go ahead and jump into this a little bit. The goal in chapter 9, you guys all watched my extra credit video, I think. I looked this morning, it seems like almost everybody did it. We're trying to solve systems of differential equations here. This is where we have more than one unknown function, right? And the unknown functions are kind of tangled up with each other, right? They're connected together by a system of differential equations. And in this box here, I wrote down the very abbreviated notation for it, right? So if you see x prime equals ax, okay, that's talking about a system of differential equations. Yeah, and the goal is, of course, to solve for the unknown vector function x. So just be really clear here, guys, this x is not a number anymore. It's not even a scalar function. It's actually a vector function. So I'll just maybe remind you over here, this x, first of all, it's a function of t. I've been suppressing the t over here. You don't see the t everywhere on that side, but this is an entire vector of functions, right? So there's an x1 of t, x2 of t, all the way down to xn of t. It's a column of unknown functions that have been expressed into a vector, you see. That's the idea. So we're hoping to solve for that, right? We're hoping to solve for this x of t right here. That's the goal. But when we do that, we're really solving for n scalar functions. Right, that's kind of the idea. The solutions, which is what we're trying to find, one good thing that we do know about them, which I included in the video that you watched, is that they do form a vector space. They're closed under addition and they're closed under scalar multiplication. They form a vector space and its dimension will be n, which is just the size of the matrix, right? That matrix is n by n. So whatever that size is, which in chapter 9, it's usually going to be 2 by 2 or 3 by 3. Whatever that size is, that clues you in to sort of what the dimension of your solution set should look like. Of course, we all remember what dimension means. It's how many vectors would be in a basis, right? It's how many solutions, how many linearly independent solutions it would take to span the whole solution set. Right, that's the idea. So we know that we need n solutions because it's n dimensional here. It's always nice to know how many solutions you have to find. That helps. And like I said, n will usually be either 2 or 3. So for the most part, you just have to find 2 or 3 solutions. Now, what's the strategy for finding those solutions? The strategy for finding those solutions, as I showed at the very end of that extra credit video, this is just a totally, I remember when the first time I ever saw this, I was just amazed by it. I was like shocked. How could eigenvalues and eigenvectors have anything to do with this? But they do. As it turns out, if we take the eigenpairs of the matrix, we can form this notation here, x of t equals e to the lambda times t times the vector v. We can build this expression. Now keep in mind, v is just a vector. It would be written as a column that has a scalar function in front of it. So that scalar just multiplies through the vector, you see, and it creates a vector function. It turns out, as you saw in my video that you watched, that if we form these x of t's, they actually do solve our linear system. They actually do solve this system of differential equations over here. And that gives us a game plan. That gives us a strategy for how we're actually going to be able to solve our linear system. What we're going to do is, first and foremost, we're going to take our matrix and we're going to find its eigenvalues and eigenvectors. That's why I kind of put chapters 7 and 9 together here, right? Because you have to do the eigenvalue eigenvector theory first, right? You have to get those eigenpairs. And then for each of these eigenpairs, we can build a solution. Now we need n of them. We need n linearly independent solutions in order to have a basis for our solution space. Okay, but as we learned in chapter 7, not every matrix has, not every n by n matrix has n linearly independent eigenvectors. Sometimes a matrix can fail to have enough eigenvectors. You remember that? It's what's called a defective matrix. That's bad. If the matrix is defective, we're not going to be able to come up with a basis worth of eigenpairs. We're not going to get n of them. So that's going to be an issue, but I'm going to save that issue until Thursday and focus today on, what is going on here? I'm going to focus today on the non-defective case. I'm going to focus on the non-defective case, and that's what section 9.4 is about. So let's take a little bit of time here and talk about the non-defective matrix scenario. So if A is a n by n non-defective matrix, so this will mean, if this is a non-defective matrix, it's going to mean that we have n linearly independent eigenvectors. So that sounds pretty good. So let me just start by just showing you a quick example so you can just see how easy this can be. All right, so for example, find the general solution to, okay, so here it is, negative 2x1 minus 7x2. Sorry, this is supposed to be equal to x1 prime. So x1 prime equals negative 2x1 minus 7x2. And x2 prime is equal to negative x1 plus 4x2. Find the general solution to that system. So that is an actual linear system of differential equations. Okay, so let's see if we can do that. Turn the screen off for now. Okay, let's see if the blue works any better here. A while back, somebody threw some water on this board, I think, and it's just made it really hard to erase. Do the best that I can. It's also had a week off to kind of become sort of hardened into whatever shape it's going to be in. The first thing is, you notice here that I did not give you the system exactly in looking like this form. You have to recognize that what you have here on the left side, that really is the x, sorry, that is the x prime of t, right? So I'm just going to rewrite this thing in this form here, capital A times x. I can put a t there as well if I want to. And then what is the matrix A? So what you have to recognize here, guys, is that the matrix A just comes from these coefficients here in the right-hand side of the system. So the first row is just going to be negative 2 and negative 7. And the second row is going to be negative 1 and 4. Okay, so it's going to look kind of like that. So that's my 2 by 2 matrix. And let's follow our strategy here. The strategy says that the first thing we want to do is find the eigenpairs of this matrix. So here's our matrix. And we all know how to do this, I hope. This is going back to chapter 7. To find the eigenvalues, we subtract lambda off of the main diagonal of this matrix. Okay, so I'm just going to subtract lambda off of the main diagonal everywhere I see it. And then this is just a 2 by 2 determinant. So we all know how to calculate that, I think. We just take the upper left corner, which is negative 2 minus lambda. The lower right corner is 4 minus lambda. And we subtract 7 from that. Okay, and because this is only a quadratic equation, I don't really get too nervous about multiplying it out, right? Because I'll be able to get the roots from the quadratic formula if I need to. So let's just go ahead and expand this out. I see that I'll have a lambda squared here. And then what else do I have? I have 2 lambda minus 4 lambda, which is negative 2 lambda. And then I have -8 and -7, which is -15. Okay, and what I'm going to do, guys, is I'm going to set that one equal to 0. This is our procedure for getting the eigenvalues, right? This factors actually nicely. It's just lambda minus 5 times lambda plus 3 equals 0. And so I get my lambda values right away. Lambda is equal to 5, or lambda is equal to -3. Those are the two eigenvalues in this case. Don't forget about your fun facts. There were some folks on the extra credit quiz that did not have the eigenvalues fitting with fun facts. The sum of these two eigenvalues, if I add them together, it should agree with the trace of the original matrix. So the trace here is 2. So when I add my lambdas, they should add up to 2. And then the product of the eigenvalues, in this case, that would be -15, should match up with the determinant of the original matrix, -15. Okay, so that kind of checks out that these eigenvalues are likely to be correct the way it looks so far. Okay. So let's take each one of these eigenvalues. I'm going to go pretty quickly through this piece of it. By the way, do we know that this matrix is non-defective yet? We do. We already know that. Why do we know that already? There's no repeated eigenvalue. Exactly. No eigenvalue. Now, even if there is a repeated eigenvalue, like there was on the quiz, right, it still might be non-defective. But for sure, if there's no repeated eigenvalue, then it's non-defective. So this is a non-defective matrix. That's what we're talking about in this section. So I have to do a little null space here, right? I have to do a little null space where what do? I subtract 5 off of the main diagonal of the matrix. So if I just subtract 5 off of the main diagonal everywhere, I'm going to get -7, -7, and then I'm going to get -1 and -1. This matrix can't be invertible, right? It cannot be because the determinant had been set equal to 0 when we solved out for that lambda. So this matrix is not invertible. Again, it's a red flag. If you don't get a free variable here, right, that's a red flag that something's wrong with either your calculations or with your lambda values or whatever, right? But here I can see that I can cross off a row. It doesn't matter which one. And I'm just going to get my eigenvector by using my little AB trick. Okay, I'm gonna skip doing the free variables and all that business. You can do it if you want to, but I'm just gonna go straight into the AB trick. That's where you swap these two numbers. In this case, that really doesn't do anything. So just swap those two numbers and then do a sign change on one of them. So this becomes your eigenvector. And guys, do slow me down if I'm going too fast on any of this, because this is all just chapter 7 review, and I just want to make sure everybody's good. But we can go pretty fast, especially on a 2x2. It goes pretty easily. Let's see, the other eigenvalue is -3. So let's take a look at the null space for that one. So I have to add 3. Okay, so remember, if this is a negative eigenvalue, it's going to have the effect of being added to the main diagonal of the matrix A. So I add 3 to the main diagonal, I get 1 and -7. And then if I add 3 on the second row to the diagonal, I'll get -1 and 7. So just adding 3 to the diagonal values of A. Just the diagonal ones only. That's the matrix I get. These two rows had better be multiples of each other. That's confirmation that we're doing it right, because you've got to have a matrix here that's not invertible. I'll just cross off a row again. Doesn't really matter which one. And then I'm just going to go straight into my AB switch trick thing. So I switch the order of the 7 and the 1, and I do a sign change on either one of the entries. So here I took the -7 and changed it to +7, and then put a 1 here. If you don't like all this finagling, of course, you can introduce free variables and solve it by back substitution, like always. I'm just kind of giving you a shortcut. Okay. And guys, that means we have two eigenpairs here. We have two sets of eigenvalue, eigenvector pairs. And each one of those gives me one solution, and I only need two solutions to my system, right? So I'm gonna get a solution here. Let's come back over here again and write down x1 of t. I'm using this setup right here, this formulation. X1 of t is going to be what? E to the 5t times the vector negative 1, 1. And x2 of t is going to be e to the negative 3t times the vector 7 and 1. It's going to look just like that. That's x1 and x2 right there. And so what is my final answer? So it says find the general solution, right? So the general solution now, I'll put that one over here. The general solution is x of t equals. Right, so I think we all know how to do this. We just form linear combinations of those two basis solutions, right? So just gonna put a box around these for a moment. X1 and x2 here, right? So then what do I put here for my final answer? It's just linear combinations of these. C1 times e to the 5t times the vector negative 1, 1. Plus C2 times e to the negative 3t times 7 and 1. That's it. That's the answer. And whether you realize it or not, I would say about 90% of this problem is just the chapter 7 material. Just finding the eigenvector, eigenvalue, eigenvector pairs. Once you've got these pairs here, then this is just writing down the answer. Now, you don't have to do this. I'm going to go ahead. I'll put optional here, just so you can visualize another way of writing. This would be a perfectly good final answer the way I've already written it. But just in case you're curious, it's acceptable to kind of read along the top slot from left to right all the way across. And if I did that, I could write this whole top line just in this form right here. So let's just look at this, make sure we understand where I'm getting that from. Just on top, if I glide across the top slot of everything, I see a negative C1 e to the 5t. And then here I have a 7 C2 e to the negative 3t. And that's just all getting added together here. And then I can, just in the same way, I can sort of ride across the bottom slot as well and rewrite that as well. So I could get C1 e to the 5t plus C2 e to the negative 3t if I just kind of glide across the bottom slot. Does everybody understand what I just did there? Is that clear? You don't have to do that, that step, but you know, if you look in the back of the book, sometimes they might write it that way. This would be the final answer. Questions here? Alex?
I remember the AB trick. I'm just a little confused over there. So is it negative B and A or?
Yeah, so if you have just two numbers in a row like this and you want to make a vector out of it, what you do is you switch the order that the two are appearing in, and then you do a sign change on one of them. It actually doesn't matter which one. So
That's
you
why I was
could,
confused because those, like I was looking at the two and on one of
Ah.
them, like on the first one you did negative 1, second one. It seems like you did.
I did it the other way around.
Yeah.
Yeah, I usually will try and do it in such a way that I have less minus signs. So,
it
but
doesn't
it's,
matter, just-
it doesn't matter. Yeah, it doesn't matter. I mean, after all, these two things are just multiples of each other. So they're equally good as basis vectors. Yeah. Angela.
For the last year problem on the homework, I saw in the textbook that the solution it wanted it written was kind of like that.
Oh,
Yeah.
um,
Was there another way to write it or?
no, I would either, honestly, this is the way I would probably write it. I was just showing you optionally that you could kind of compress it into a single vector here. It doesn't really matter to me though. Yeah, I think it, now on the homework for today, you're not doing any of this. On the homework for today, you don't have to actually find the solutions. They should have given you the solutions in section 9.3, they sort of say, here's x1 of t and here's x2 of t. They give you these and they just ask you to check them, that they work. That's all you have to do. Like, by the way, how do you check them? Checking them just means take the derivative of what they gave you and compare it with what happens if you take the matrix times what they gave you. You should get the same thing. That's how you verify that something is a solution. Maybe I can take a look at that problem in a little while, but yeah, I don't think you're gonna have to ever put it in this form. Exactly. Other questions so far? Marco.
So, in this case, I can't figure out, but what would a defective A look like?
Well, a defective matrix here, you'd have to have a repeated eigenvalue that did not pull its weight. And if it did not pull its weight, then you wouldn't be able to get n eigenpairs. And so you wouldn't be able to get enough solutions to sort of make a basis for your n-dimensional solution space.
So during the exam, would you tell us just to find the general solution and we'd have to figure out like this whole process before like solving?
I'm probably not gonna tell you if the matrix is defective or not. You're gonna figure that out. What do we do if the matrix is defective? If the matrix is defective and we don't come up with enough eigenpairs, then we have to learn something new. And that's for Thursday. So that's section 9.5. I'm gonna save that for Thursday. Like, what do we do if the matrix is defective? Okay, any other questions so far? Of course, if they gave us an initial condition here, if they told us what x1 of 0 and x2 of 0 were, then you would be able to plug in t equals 0 here and solve for, see, if you plug in t equals 0, the exponentials go away and you just get a little equation involving C1 and C2. And so you'd be able to solve for C1 and C2 if you were given initial values. Now, in this problem, I didn't do that. I just said find a general solution. There's no initial values here. But if you're wondering, how do we figure out what C1 and C2 are? You only solve for those if they give you an initial value that allows you to do that. Here, we don't have that information. Alex?
So I think, yeah, on 9.3, they add, or it says like if there is solutions.
Uh-huh.
When we do that, we like by checking it, end up with something like that and then be able to solve it.
Yeah, exactly. It's just that in 9.3, they're basically going to give you these two things. We derived them using our understanding of eigenvalues and eigenvectors. But in section 9.3, which is the homework that's based on the stuff before today's lecture, they're not expecting you to come up with these, right?
I think it's just something about like a basis or a general solution.
Yeah.
And then like I read in the textbook before that.
Uh-huh.
If you find that there's Li, you can use.
Yeah.
directions, and that's what they put it in that.
Yeah, so if they gave you, oh, I see that. Yeah, so they give you the x1 of t and the x2 of t, and then they do say, find the general solution of the system. So you realize all you have to do there is literally write it down. X of t equals C1 times the first thing they gave you, plus C2 times the second thing they gave you. Just write it down. You don't have to show any work. You don't have to do any extra count. It does say to verify Li. Now that would involve using the Wronskian that I mentioned in my video. Okay, but in terms of what you're writing down for the general solution, you can literally just lay it down. Yeah. Anyway, maybe I'll come back and do number 2 in a little bit to make that very clear. So what I want everybody to understand here, though, is that this solution, this general solution to our system, is not just one solution. It's an infinite family of solutions. Because after all, I have infinitely many choices for C1 and for C2. Every time I pick a C1 and a C2, I have another solution. Right? So what I actually would like to show you guys is how we could visualize this. It's easy enough to kind of go through the motions, crank out the calculations, but what does this mean physically? I would like to show you what I would like to do here as a sort of what I'll call a follow-up is the follow-up is going to be to do something where I'm going to draw what is called the phase portrait. Okay, so this is a new idea as well. I have not talked about this before. I would like to draw the phase portrait for this system. Okay, and now how is that going to look? First of all, I'm going to mention here that this is going to be for 2x2 systems only. I won't ask you about 3x3 or larger systems like what you would do. So this is only for 2x2 systems. But the idea here, I'm going to go ahead and erase this secondary version of it. The idea here, guys, is that you would draw this picture. So I'm going to make some big axes here, and I'm going to label these axes with X1 and X2. Give yourself plenty of room. If you're taking notes on this, give yourself plenty of room to kind of draw a set of axes. I'm going to sort of make some tick marks here along my axes, and I'll show you how we're going to draw our phase portrait in just a second. So a phase portrait is literally a picture that is drawn in the two-dimensional Cartesian plane, okay? And what we're going to do on that coordinate plane is we are now going to draw some representative solutions to our system. Now, remember, a moment ago, I told you that there are infinitely many such solutions because there are infinitely many choices for C1 and C2, right? So I'm not going to draw all of them because I can't draw infinite solutions. I'll be here for the rest of my life. So instead, I'm going to pick and choose a few of the solutions to draw. And there is no better place to start than with the two basis solutions that we had looked at in the first place. So let's take a look at this x1 of t for a minute. And I would like to imagine that at time 0, okay, so this xy plane, I want you to imagine that it is the surface of the ocean. It is a lake or an ocean. It's got water in it. And we are going to drop a feather onto this ocean at time 0 at whatever the point is. So if I plug in t equals 0 here, the e to the 0 goes away and I just get -1, 1. I'm going to drop this feather at the point -1, 1 on the surface of my ocean. And then what I'm going to do is I'm going to watch what happens to the feather as time goes on. So t is time here, right? So what happens as t increases? So starting at t equals 0, we just have -1, 1. As t increases, what happens to this is the vector -1, 1 gets scalar multiplied by this e to the 5t, which is getting bigger and bigger and bigger as I go, right? So would you agree that essentially the vector, the point -1, 1 is just going to get stretched? That vector is just going to get stretched. So later on, the feather is going to be there, and then it's going to be there, and then it's going to be there, and it's going to flow out towards, well, if I draw it well, it's going to flow out towards infinity. So imagine dropping a feather onto this ocean surface at time 0 and letting the feather float into the future according to the currents of the water. Right, so if I drop the feather right here, it just flows out that way. Does everybody agree with that? Right, when t is equal to 1, then what's my vector? My vector, when t equals 1, my vector is -e to the 5th, comma, e to the 5th. Well, that's just somewhere up here. I don't know exactly. Gilbert?
How did you determine like that direction?
Because if I start with the feather right here at time 0, and then later, as t gets bigger, right, this exponential function is growing, it is blowing up, which sort of makes these numbers here swell up, right? So the vector gets much bigger and bigger. Agree with that?
Yeah, thank you.
Okay, sweet. Good point. It's a very good point. Let's take a look at the second solution. At time 0, I'm going to drop my feather onto that picture. And where is it going to get dropped at? 7 and 1, right? At t equals 0, that corresponds to 7 and 1. Where is 7, 1? 1, 2, 3, 4, 5, 6, 7, 1. Okay, so now I'm going to drop my feather right there. I'm now drawing a second solution, right? So this first one, by the way, this thing here, this is just x1 of t. It's just my first solution that I should put a vector on that though, sorry, x1 of t, it's a vector function. Now I'm drawing the second one. And if I put my feather right here at time 0, and now I want to watch, where does the feather go? Where do the ocean currents move that feather as time increases? What do you guys think?
To 0.
Say it again.
To 0.
It goes towards 0 this time. It gets back to Gilbert's point just a moment ago. See here, this is negative 3t. So as t increases, e to a negative, bigger and bigger power is going towards 0. So this feather, if I start the feather there, this feather is going to come in towards the origin. And by the way, I can go backwards in time. So if you imagine t was negative something, that would just reflect the fact that the feather could have been way out towards infinity and then sort of floating in along that straight line. Clear enough? So this one is x2 of t. Yeah, Marco?
In this case, is t a function of time? Because if you did -1 or -3 for t, wouldn't that be going in the opposite direction from the time?
Yeah, if we put in a negative value of t, like -1, then this would become e cubed times 7, 1, which would be
Pointing in
that way. The arrows are just showing you which direction the feather moves as time increases. Right? That's all it's showing you. Okay, so far, guys, I have drawn on this picture 2 of the solutions among my general solution that I have here. I'm going to draw a few more. I have one really easy idea, which is, why don't we draw the negative of x? See, I can take any linear combination of x1 and x2. So I could take x1, right, and just put a minus sign in front of it. Just choose C1 to be -1, and don't worry about C2, just make it 0. Well, that's just literally the negative of this solution, and that is going to be a mirror image of that solution down here. This is negative x1 of t going in that direction. It's literally just flipping the picture around. So if I choose to drop my feather in right here, right, it's going to sail that way as time goes on. Marco.
So you said for the general solution, there's infinite many solution based off of C1 and C2.
That's true.
But based off of what we did with that AB rule for the vector,
Uh-huh.
we can have 4 different graphs based off of what. So what is that supposed to represent?
Well, if I chose this one instead of this one, then at the end of the day, it won't make any difference because there's going to be a constant. It's like if I put 1 and -1 here, then that just reverses the role. So then the C1 equaling 1 would give me this curve. Like this would then become x1 of t, and this one would become negative x1 of t. But as a pair, they're the same 2 solutions. It doesn't actually make a difference in terms of the collective totality of all of the curves that you could have. So what did I just do? I don't want to mess this up. Yes. I just didn't have a lot of room here. This does backfill. If we run the camera in reverse time and then we allow t go to negative infinity, the feather that showed up right here, if you roll the camera in reverse, that feather is going to very slowly and asymptotically approach back to the origin. It's never quite going to get there though, but that's essentially what it's doing. Yeah.
But it's separate from the negative.
Yeah, these are 2 different solutions for sure. And I'm going to do the same thing with x2. I'm going to take the negative of that one, which would be coming from this side with the arrows again kind of going inward here. Okay? So that would be like negative x2 of t. So far, guys, so far on that picture, I have drawn four. I have drawn four solutions out of the infinitely many that there are, right? I've just only drawn four of them. I mean, because you might be wondering, what would happen if I drop the feather in right here? Right? I could drop my feather onto the ocean right here. Where's the feather going to go now? Well, it turns out that if I start my feather off right here, then it's not living on either one of these eigenspaces. We now actually have some kind of a combination. It would be a legitimate linear combination of both of these terms with non-zero values for both of the constants. But the visual idea behind what the phase portrait is going to do is this feather is going to follow a curve. It does not need to be perfect, guys. Unless you use a computer, it will not be perfect. But the arrows of what that feather would do should be somewhat consistent with the way the arrows are already on the picture for the four curves that I do have, right? So I could have, guys, all of these, every single one of these that I'm drawing is a legitimate solution to my system of differential equations. Remember, there are infinitely many. And it's only after I give you an initial value, right? If I give you an initial value and I say at time 0, my feather is here, right? If I do that, well, that pinpoints this curve specifically from the infinitely many curves that we have here, right? We can specifically pinpoint one of them with an initial value. And an initial value basically is, I'm telling you where the feather starts, where I've dropped the feather into my picture, right? What about over here? What if I drop the feather right here? Well, again, kind of take a look at the curve, the arrows and the curve we already have. This feather is going to do something like this. It's going to essentially be moved in a manner that is compatible with the arrows that are already here. Here's another one, right? Here's another one. And we can just go in and fill this in. And this is kind of what a phase portrait looks like. You can pull up MATLAB or Mathematica, have it draw a beautiful phase portrait for you that's exactly precise. Here, a rough idea is really all I'm looking for. So this is called the phase portrait of this system of differential equations. Again, only for a 2x2.
Put a 3 by.
It would be, yeah, it'd be a three-dimensional one, so it would be very hard to draw. Yeah, exactly right. Now, there is a name for this type of phase portrait. This is called, this is what is called a saddle. This is a saddle. It kind of looks like it. I don't know if you remember from your Math 250A, your multivariable calculus class, but you would have been drawing level curves to surfaces. And one of the surfaces that you learn about in Math 250A is the hyperbolic paraboloid, which is so hard to draw. But if you want to know what a hyperbolic paraboloid looks like, just go take a saddle that you put on a horse, and it is shaped, or you can take a potato chip, is another good example, and just taking those shapes, those are hyperbolic paraboloids, and when you slice through them and form the level curves, they actually look a lot like the picture that we've seen here. It's just that in Math 250A, there's no time component to it. It's just literally a dead curve that sits there. Here, we actually can think about the evolution of this picture. If I drop the feather somewhere, then as time goes on, it traces along one of these curves. By the way, none of these curves over here should ever intersect. They never cross each other. So if I drop my feather right here and Eduardo drops his feather right here at the same time at time 0, and we watch our feathers go forward with time, our feathers are never going to collide. They're never going to crash into each other. Something about there's a unique solution to the differential. I mean, if I have values for C1 and C2, then that determines a unique solution. So I shouldn't have two different feathers that kind of crash into each other at some time in the future. That never would happen. So before we take a little break today, just wanted to point out that the real driver of what this picture looks like is actually just the eigenvalues themselves. Do you notice that one of them is positive and one of them is negative? And that's why one of the eigenspaces has arrows pointing inward. That was the one corresponding to lambda equals -3. And the other eigenspace has arrows that are pointing outward. That's because when lambda is positive, then when time goes on, the vector gets stretched out to infinity, right? So your feathers go away from the origin when there's a positive lambda value. But when there's a negative lambda value, they tend to come towards the origin. And that's what gives us this saddle. But you might be wondering about some other possibilities. What if both of the eigenvalues were positive? Or what if they were both negative? Let's jot this down. Other possibilities. If both lambdas, there's going to be two of them presumably, right? So if lambda 1 and lambda 2 are both negative. So just imagine with me for a second, guys, if they were both negative. That would be like there was a minus on this 5 as well. They were both negative. Then all of the arrows would be going inward. Right? If they were both negative, then all of the arrows would be going inward. And in fact, it doesn't matter where you put your feather, it's always going to float towards the origin, right? So in this case, the phase portrait is what's called a sync. And I'm going to draw a little picture of it here, just a mini picture. I'm not going to do a full-blown example of it right now, but I'm just going to draw you a mini picture of it. But essentially what it is you'll have two different eigenvalues and eigenvectors, but everything is negative. So all of the arrows are going inward. And it doesn't matter where you drop your feather. The feather will always tend to float towards the origin. This is what the phase portrait of a sync will look like. Everything goes towards 0, 0. Guys, imagine if this was -5 right here. I don't care what C1 and C2 are. As time goes on, if these were both negative, as t goes to infinity, this vector is going to get killed and this vector is going to get killed as t gets bigger, right? Because e to a negative huge power is like 0. And you're killing this term, you're killing this term. And so everything is killed and the vector is basically going to become 0, 0. That means that I don't care where you drop your feather in on this phase portrait, as t goes to infinity, that feather is headed towards the origin. Exactly right. Okay, so that's another possibility. Let's write down one more here, guys, and then we'll take a little break. What if both of the lambdas are positive? What if both of them are positive? I'm sorry? Then all the arrows are going outward. It's like the sun with its rays of light going away from the sun in every direction. And this is called a source. So we have saddles, we have sinks, and we have sources. And I don't have a lot of room. Maybe I'll draw it over here. Is it okay if I draw over here? Can everybody see? Just going to draw the picture over here. It's just exactly what you think it would be. All of the arrows going outward. All right, so that's an example of what a source would look like, roughly. I always get the question from students to say, well, how many curves do I need to draw for my phase portrait? And my answer to that is usually just a few, just enough that you can kind of get an idea what the picture looks like. But the key thing here, guys, the key thing is that the difference between this picture and this picture And this picture is simply whether the eigenvalues are both positive, both negative, or one of each. So I've been known to do this on my exam. I give you three matrices, three 2x2 matrices, and I give you three pictures. And I ask you, match up which matrix goes with which picture. And what the students have to realize is that they only have to find the eigenvalues to decide that. Right? Because if I have two positive eigenvalues, that's got to be a source. If I have two negative eigenvalues, it has to be a sink. And if I have one of each, it has to be a saddle. And that's actually all you have to know. Pretty easy. Except there's a problem. There's always a catch. And that is that we learned in chapter 7 that the eigenvalues could potentially be complex numbers. We could actually have imaginary numbers for our eigenvalues, and that's already sort of a problem. I go, how am I going to draw a phase portrait for that? Ugh. I think I need a 10-minute break before I answer that question. So we'll talk about what to do for complex eigenvalues after we take a little break. Let's take 10 minutes to decompress, stretch your legs if you need to, and then we'll come back and talk about that.
I don't remember, but I remember going, oh, I'm paying for that. I don't remember exactly what it is, but I was like, you know what, that's worth it. I think it's the auto backup that it does. I think you have like unlimited notes. I don't know, but honestly. I had a bunch of different apps that I tried. I liked the Notability.
Okay, guys, why don't we go ahead and try to get back together here. Are you guys all following me okay today? So far? Because my voice is, I don't know, when you climb the mountains in dry air and you're breathing really heavy, you get this like exercise induced asthma or whatever. And so I came back with like really hoarse, dry throat. And was having a lot of trouble just even talking yesterday. Doing a little better today, but I brought my water. And I'm hoping that I'm making some sense up here. They also say that your brain can kind of go foggy at high altitude. So I'm hoping my brain is back to normal by now and that I'm making a little bit of sense here. Yeah, so before I go any further, just a quick reminder, we have some homework due tonight. There'll be one more assignment due on Friday night, and that's going to cover the stuff that we're doing today and Thursday. I have one other request for you for this week, though, in addition to that, which is that this is the last week that you guys can fill out an SOQ for this class. They've had this thing open for almost a month now. And so I wrote you an email a while back saying I'm going to give extra credit for people to fill that out because we're not going to have any videos for the final to watch or anything like that. So I'm going to give everybody in the class an extra 3 points on the final exam, provided that you guys all collectively manage to get 90% of you has to fill out an SOQ form. And keep in mind, there's a couple people who are sort of semi not in the class anymore. They're kind of just not really doing it anymore, which basically means I need everybody who's still coming to do it, and we can get there. I checked this morning. I think I can't read the SOQs yet, but I can tell how many people have filled them out, and it's about 60% right now. So we have about 4 more days to fill this thing out. So for the 30% of you or so who have not done it yet, please do it, because otherwise your classmates are going to be upset with you, and they're going to be poking you to fill those out.
I know where you go to school.
Exactly. And I really do appreciate the feedback. It's a chance for me to find out what I'm doing well, what I'm maybe not doing so well, anything you have for suggestions or things you think, oh yeah, you should keep doing that. It's really good, whatever. I will definitely read and take into account your comments. Like I've made a lot of changes just based on SOQs. So it's actually something I take seriously, like giving 3 midterms instead of 2. That was something the students asked for. Recording these lectures and putting them on my Canvas page. I didn't used to do that. So if you have other ideas or just things you think I should keep doing for sure, let me know. If you like the extra credit videos or the extra credit quizzes, this is actually the first time I've tried doing extra credit quizzes. So just let me know. Anything that comes to mind, you can fill those out anytime this week. Okay? Thank you in advance for that. Let's try one more example here. I'm going to go slightly faster through some of the basic parts of this problem. This is another problem, just like the one we did a few minutes ago. It's a 2x2 system. And I am going to just give you a hint here of what the lambda values are. I'm not going to derive them because I think you guys can all do that at this point. The lambda values turn out to be 4 plus or minus 2i. Okay? And you can always check that with the fun facts, right? They have to add up to the trace of the matrix. If we multiply 4 plus 2i with 4 minus 2i, we should get the determinant of this matrix, which I think is 20, and so on. Okay? But anyway, so this is one that when you get the quadratic equation for the characteristic polynomial, you would actually use the quadratic formula to get these two roots. Okay? So this is totally doable. I'm just skipping the details so that we can get right into it. Let's take a look at 4 plus 2i. That's the eigenvalue I'm going to work on first. And we're going to do a null space here. As usual. So the way this works is we subtract the eigenvalue from the main diagonal. So I go to the main diagonal of the matrix and I subtract 4 plus 2i from every entry on the diagonal. So if I take 9 and I subtract 4 plus 2i, I will end up with 5 minus 2i. Be very careful with your signs, pluses and minuses on this. 29 stays the same, and then this -1 stays the same. But then in the lower right corner, I take -1 and I have to subtract 4 plus 2i. So that's -5 minus 2i, something like that. Now, I know that it doesn't look like it. It's not as obvious to us because of the imaginary numbers that are in this matrix, but you have to trust the theory that tells you that these two rows have to be multiples of each other. It's just that the complex numbers have made it less obvious than it was on the first example today. But the theory is the same. I've got to be able to cross off a row. So I'm just going to cross off whichever row I want. And what I'm going to do then is I'm going to use my AB trick on the row that I didn't cross. By the way, if you cross off the bottom row, that's not wrong. It'll just give you a different eigenvector. Totally okay though. I'm just going to keep this bottom row and I'm going to do my AB switch trick. So this is where I write the numbers down in the reverse order and I change the sign of one of them. So I'm going to take the -5 minus 2i and write it as 5 plus 2i. So I did a sign change on that. And then the -1, I'm just literally copying it over. Okay? Is everybody following that? This is the A and the B. And then this is just -b and A. Okay? Now, for reasons that you'll see in a minute, I actually want to take this vector and split it, kind of like busting out the variables, except it's not really a variable. But I have an I in here, and I actually want to kind of bust that out. So I'm going to take the 5 and the -1 that does not have an I and leave that as one piece. And then I'm going to add, what will it be? 2 and 0 times I. So we see that there's an I in the top slot here that has a 2 in front of it. So that if I read along the top line, I get 5 plus 2i. If I go along the bottom line, I just get -1. Okay, so you're going to want to kind of split it out like that. You'll see why in just a second. Okay, now what my theory told me was that I can then build out of these eigenpairs, which we have, we can build solutions to our equation. So I'm going to actually denote this. You'll see why in a minute. x1, 2 of t. This is not a 12. This is a 1, 2. And you'll see why I'm using this notation in just a minute. But you guys remember, right? You remember what we're trying to do. We're trying to write x equals e to the lambda t times v. That was how we were making our solutions. So I'm going to do that right here. E to the lambda is 4 plus 2i times t, and then times my vector, which, let's use some big parentheses here, sorry. Make some parentheses, and then I'm gonna put 5 and -1 plus 2 and 0 times I. So just like that. So this is just e to the lambda t times v. This is my v vector right here. Okay? Everybody with me so far? Now, of course, you know what I'm gonna say next, which is, of course, this is fine, except that we're not really happy to have I in our answer. It's imaginary. This would be, again, I talked about this in chapter 8. I wouldn't know how to plug numbers into it. I wouldn't know how to graph it. I wouldn't know how to make physical, real world sense out of it. It's not the kind of an answer that an engineer is going to be looking for, right? So what we were going to try to do now, guys, most of the focus of this work is just going to be to get rid of the I, right? And we do have at least something we can do, which is I can take this e to the 4t and put it in front. So I see e to the 4t. And then I have e to the 2it. And we hopefully remember from the last chapter that that can be decomposed using the Euler formula, using sines and cosines. So does everybody remember that? Right, so just recall this, e to the I theta, right? We did this about a month ago. Cosine of theta plus I times sine of theta. So I'm just doing that right here with the theta value of 2t. Let me know if I'm going too fast. I'm just basically trying to use that Euler formula there. And I'm not done yet. I've still got to write down, I've still got to write this down. 5 and -1, and then plus 2 and 0 times I. That part's still there. Just have to recopy it again. Okay, I have not gotten rid of the I yet, as you can see. But I am getting closer. So let me go over here and continue. x1, 2 of t equals e to the 4t looks great. I'm happy with that. But now, what about all this stuff? This is sort of like, you know, a plus b times c plus d, right? You have something plus something times something plus something. And so if you had that in an algebra class, your knee-jerk reaction, without even thinking about it, is probably going to be, oh, I'm going to FOIL it out, right? And that's exactly what I'm going to do. I'm going to FOIL these terms with these terms, except that I'm not quite going to FOIL them. I'm going to FLOY them out. I'm not going to FOIL, I'm going to FLOY. And I want to explain why. So you know what the FOIL stands for, right? Firsts, outers, inners, and lasts. But I don't want to do it in that order. I'm going to do the first part first. So let's get some parentheses going here. The first parts would be cosine of 2t times the vector 5, -1. Okay, so I'll just put F there because that's the first. So I'm doing the first term with the first term. Okay, now normally we would now do the outer term and then the inner term and then the last term, but I'm going to do FLOY instead of FOIL. So the last term would be the I sine 2t and then 2, 0, I. I'm going to multiply that together. And what is I squared, by the way? -1, right? I squared would be -1. So you're going to see a minus sign here. And it's going to be sine of 2t times 2, 0. Okay? And that's the last. So that's first and last being put together. Does everybody understand? The minus sign is because I times I is -1. But so far on this board over here, I don't have an I in it, which makes me happy. Let's actually put some extra parentheses around that piece. Okay, and then I'm going to keep going. And what I'm going to do next, guys, let's add a few more parentheses here. I'm going to do outers and inners. So this is why I'm calling it FLOY instead of FOIL. The F and the L are getting lumped together. Why did I lump them together? It's because there's no I in either of these two terms, which I'm happy to see. Right, there's no I there. Now, what happens though when I do the outers or the inners? Ooh, both of those are gonna have an I on them. I'm gonna factor it out. And when I do the outers first, I have cosine of 2t times the vector 2 and 0. And then finally, I'm gonna add the inner term, which is going to be sine of 2t times the vector 5, -1. So it's gonna look like that. And then I guess I need a really big parentheses on that far outside of all of that. Okay. Well, we have not quite gotten rid of the I completely, but we're doing pretty good. The only place I have an I now is right here. And we have to also remember that we're only looking at 4 plus 2i. It turns out, I'm not going to prove this, but it turns out that if I go back now and I start over with 4 minus 2i as my eigenvalue, and I do everything the same way again, and I work all this magic, the Floy thing and everything again, what I will get when I do the other eigenvalue is literally this thing again, except with a minus here, as it turns out. And because of that, you can of course then imagine taking those two solutions and forming linear combinations of them, right? And in so doing, you can extract two real solutions. So let me just write that down. So we extract two real solutions. So I'm going to omit some of the technical details and just kind of get to the punchline here. The first one, which is x1 of t, is literally just this first part. So e to the 4t times cosine of 2t times the vector 5, -1 minus the sine of 2t times the vector 2 and 0. Okay, that's one solution. It's literally just coming from the FL part, the Floy of the Floy, the F and the L part. It's literally just ignore the imaginary piece. Okay, and then my second solution, I'm going to obtain that one. Again, I have this e to the 4t because that's been factored out of everywhere. And I'm going to grab all of this part, but not the I. So I will just grab cosine of 2t times 2, 0 plus sine of 2t times 5 and -1. And that's coming from the outers and the inners. The outers and inners terms gives us those. So this is x1 and this is x2. And so you can, well, that's what you needed, two solutions, right? It's a 2x2 system. I need to find two basis vectors, and these are going to be those two basis vectors. Yes.
If you rearranged it into a matrix, would it still be, it's still a 1x2 matrix?
Yeah, you could again compress the terms here. So again, I'll just come over here. I'll just call this optional. It would be totally okay, but it is optional to kind of just put this part that's in the parentheses into a single vector. So on top, we would have 5 cosine of 2t minus 2 sine of 2t, right? And if I read along the bottom line, I would have just negative cosine of 2t. So that's optional to rewrite it like that. If you want to, you can. And the one on the bottom would be similar, e to the 4t, and then again, if I compress everything, 2 cosine of 2t plus 5 sine of 2t on the top line. And on the bottom line, I would have negative of the sine of 2t. Okay? And this is going to be our basis. Technically, if you really want to harp on it, technically, I should use the Wronskian and make sure that these are Li. We're not going to take the time to do that. It would actually be kind of a mess. Is that a hint?
Yeah.
Yes.
So why would x2 of t Why would that be a real solution if there's an I next to it?
So the I actually goes away when I go back, if I go back to the other eigenvalue. And I work this whole magic again, and I have another term that has a minus sign on it. What I'm actually doing, I'm not literally just plucking this off. I'm not allowed to do that. Instead, what I'm doing is I'm saying there would be another solution that would have a minus here. All of this the same, minus all of this the same. And then if you add those together or subtract them, you can kind of cancel off either this part or this part. And then, you know, you can divide by I at some point. I'm leaving out some of those. So I would recommend for the time being, just take my word for this, that you can basically strip off these two pieces of the solution without the I in them. If you really want to, I'd be happy in my office hours. I could like actually show it to you how that comes out. It's amazing, but it's a little long to write it all out. So, okay. So then what's the final answer, guys? The final answer for the general solution. The general solution then just becomes x of t equals c1 times x1 of t plus c2 times x2 of t. That's it. And you remember back in chapter 8, I sort of said, well, if you don't want to write it all out again, as long as you clearly identify these two solutions here, as long as I can find them in your work easily enough, and you've labeled them as x1 and x2, I will allow you to just write this down without recopying all of this again. Okay, if you prefer to write it all out again because it just makes you feel more comfortable with it, that's totally okay. But that's basically good enough for the final answer. Kind of get this, guys? Kind of understand it? I want to talk about the phase portrait for this really quick, and then we'll hopefully have maybe 5 minutes to do a couple of the homework problems. But what would the phase portraits be? This is a little bit, well, it looks a lot messier, doesn't it? But it's actually not as hard as you might think. Let's draw the phase portrait here. It turns out that, again, to draw this picture, I only have to know what my lambdas are to have the rough idea of it. So you remember, if both lambdas are positive, we had a source. If both lambdas were negative, we had a sink. And if we had one of each, it was a saddle. What about now, when the complex numbers are here? Well, I want us to look at these two solutions for a second. If the e to the 4t was not there, just forget about the e to the 4t for a minute. Do you agree that the vector part that's in the brackets will end up sort of, if I drop the feather in at time 0, do you agree that after what, 2 pi units of time, the feather would be, again, if I ignore the exponential part, do you agree that the feather would be back where it started again?
Yeah.
Sine and cosine are periodic functions. They repeat themselves every so many units of time, right? So this feather, wherever you dropped it in, just say you dropped it right here, right? It's going to do something for a while, I don't know, but it's got to get back to that same point again. Except that the e to the 4t, now I want to bring that back into play, that stretches the vector out. So if this was the original vector showing me where the feather was initially, then by the time that we go through one period, oh geez, it's bad. By the time we go through one period, the feather isn't literally going to be there. It is going to have been stretched farther out. It's still pointing in the same direction. And if we continue to let time go forward, right, this thing has to get back to the same point again, but just stretched further out, right? And let's just put some arrows on this. So the feather is actually spiraling outward. So we have a saddle, we have a source, we have a sink, and now we have a spiral. And this is actually called an unstable spiral. It is an unstable spiral because if you drop the feather in, as long as you don't drop it right at the origin, right? This feather is eventually gonna go out to infinity. That radius just blows up because of the e to the 4t. And that's really because we have lambda of the form a plus or minus bi, and the a is greater than 0, right? That a being greater than 0, the a is 4, right? The a is the 4. That's what's causing the spiral to get bigger as time goes on. Okay, so you can probably take a guess at it, guys, that if lambda was a plus or minus bi with a less than 0, so if this was like a negative 4t here and here, you would still get the circular periodic behavior of the path, but now the feather is getting sucked closer and closer to the origin all the time. This one is what's called, we have what is called a stable spiral. Okay, so, and again, I'm just going to draw a very brief picture of it. So this is a spiral that comes in towards the origin. By the way, guys, let me be very clear about this. If I drop my feather right here, and Eduardo drops his feather right there at the initial time, his feather is also going to make a spiral, but it will never overlap my spiral, right? The feather will trace out a path that is qualitatively the same, right? It'll just be a different spiral. So you just kind of have to imagine all of these spirals kind of like interspersed within each other, but they never cross, right? So, we could have Marco drops his feather right there, right? Well, he'll have another spiral, right? But his feather will never cross with Eduardo's feather or with my feather, right? They're all going to be independent of each other. Yeah.
Similar questions when I asked you about the circle. Would it be like a whole different set of things in order to determine like whether this is spinning clockwise or?
Okay, Marco's bringing up a really good point, which is how do I know that this thing is spiraling like counterclockwise as opposed to the other direction? That takes more analysis. When you take Math 310, they will spend a lot of time focusing on phase portraits and those kind of details. What you would really need to do, to be totally honest, is you would need to take a look at the derivatives of these curves to figure out what's the rate of change. Is it, so if I start right here, right, you notice that the y value, the vertical component is getting bigger initially. But maybe when you take the derivative, you find out, actually, the y value has a negative rate of change. It should be going that way instead. So you can sort some of those things out by using the derivatives of these functions. But for right now, I'm not going to hold you accountable for that. All I want you guys to know is this and this. And then, of course, there is one more case, and I'll write it down here at the very end. I think I can squeeze it in right here. If lambda is equal to just plus or minus bi, in other words, if a is 0, that would just mean that you don't have the e part at all. The exponential part isn't even there at all. In that case, if the e part wasn't there at all, then this vector would actually drive the entire curve, and it would just be periodic. The feather would just keep going in a circle, right? We have a circle. Now, it's called a circle. The radius of the circle would depend on where you dropped the feather initially, right? The initial condition. That would be the key, right? But it would literally just be a circle. Again, I'm not gonna worry about whether it's clockwise or counterclockwise. I just want you to know that it's a circle. So what do we have? We have saddle, source, sink, unstable spiral, stable spirals, and circles. Those are the 6 different qualitative phase portraits that you can have. And it all comes down to just what are the lambdas? The details of the null spaces and the solutions, you don't really need that. Does anybody have any questions on the FOIL, or I should say the FLOY method here that we used to solve this? Jason?
What if you have a lambda that's 0?
Okay, if lambda is equal to 0, great question. If lambda is equal to 0, then all of this is kind of out the window and you would just need to like analyze it on a case by case basis.
Okay.
Yeah, there wouldn't be a one size fits all answer. So I've done a pretty good job of covering this section. I've done a pretty bad job of answering any questions about the homework. You know what I'm gonna do? I am going to make a video. I'm gonna just go down to my office and I'll make a video and I'll solve those 4 problems in the video. Does that sound fair? Is that reasonable for getting some help with the homework? Don't forget, guys, I do some office hour tonight after 5:30, if you wanna come by, we can also talk in person, seems part of the quiz. And also, one last thing, and I'll get to your question in a second. On this take-home quiz, I wanted to go over this take-home quiz as well, but I'm not gonna have time right now. Just a second, guys. I am probably going to go over this take-home quiz in the review session on Sunday, Monday. And if you want to, though, the solutions are in the resources folder. I don't think anybody got everything perfect on the quiz. So it would definitely be a good idea to review that and ask me for help if you need it. Okay, guys, that's it for today. I will look forward to seeing you again soon.
So,
Yes,
our finals on a Tuesday or a
I
Thursday?
think this class is on Tuesday.
On your syllabus, on your syllabus, it says December 17th for morning class, Tuesday, but it says Thursday, and it's December 19th, also Thursday.
I'll check that again. I think this class is on Tuesday and my other class is Thursday.
I looked at it. Yeah, it's Tuesday.
Yes.
Like officially.
That's both if you want to. Yeah, not a problem.
For sure. How did that be?
Yeah. That was one we did in the class.
Yeah, you did it in here.
I just thought you.
Or did I say take?
Yeah.
Oh, no, I meant in class.
Okay, yeah.
I said sorry.
Okay.
I misspoke.
Okay, thank you.
Yeah. Not, doesn't have to be super nice. It's just whether this is a positive or a negative. As to whether it's going outward and inward. I didn't mean to draw it with different amounts of squiggling. That's too much detail
Okay.
for what we would actually be expecting to know.